It is 3:01, and we will get started. I'd like to start off by introducing myself. Hello, my name is Lance Zurich, and I am the product manager for the fischertechnik division over here at Studica. And today I'm going to provide you with an overview of the fischertechnik robotics line of solutions. And this webinar presentation is going to provide you with a look at both the line of fischertechnik education instruction sets that are used for exploring different aspects of robotics. This would be things such as electro-pneumatics and, of course, IoT, the world of the Internet of Things, as well as the line of pre-assembled simulation models that are used for vocational training, higher education, and for demonstrating various industrial processes. So, let's get up where to go here. So the question might be, what is fischertechnik? Well, just to provide you with a really brief introduction, fischertechnik is a flexible and innovative construction system. And what makes it different than other popular construction sets that you'll see that are out there is a lot of them are designed to simply stack. Instead, fischertechnik was created with more of an engineering mindset. What I mean by that is that the core building block in the fischertechnik system is unique in that it allows attachment from all 6 sides, and it thus allows for almost limitless design possibilities. Now, many of the parts are designed also to slide together and lock in place, basically using friction, and the hundreds of different parts available will also help you to address very specific design needs. Fischertechnik was created back in the 1960s by German inventor Arthur Fischer, who's noted for countless innovations used in both the construction and the automotive industries. Now, Mr. Fischer, at the time of his death in 2016, held more patents in his name than Thomas Alva Edison had amassed during his own lifetime. Well, besides fischertechnik, Mr. Fischer was the inventor of synchronized flash photography, and this was back in 1949, and he is also credited as the creator of the expanding nylon wall plug, which is usually used in conjunction with a screw or a bolt to anchor heavy objects to walls. His company, the Fischer Group, employs thousands of people worldwide, producing many variations of fastening devices used in building construction, and they also produce numerous components used in the automotive assembly process, as well as providing consulting services in regards to various state-of-the-art manufacturing processes. Now, I'd also like to point out that fischertechnik was the very first construction set of all the construction sets you know, and you probably know many by name, that allowed students the ability to build and program their own robots, and this was using the original pre-Macintosh era Apple computers. Now, almost since its inception, fischertechnik has been used by middle schools, high schools, colleges, and universities all around the globe to explore STEM-related concepts. And by this, I'm referring to things such as renewable energy, mechanics, pneumatics, and so on. Now, fischertechnik has also been used by numerous companies like Porsche, Daimler Chrysler, and BMW, just to name drop a few, for industrial simulation and training purposes. Now, recently, we've also seen many of the top companies at the cutting edge of developing IoT applications, aka the Internet of Things, using these same simulation and training models to demonstrate and study various IoT-related processes. So as such, more than being just something that students are only going to use for a year or two in their development, you should really think of fischertechnik as being designed so that students can grow along with it. So as students progress through their academic careers, they can also progress through the levels of fischertechnik education solutions which are available. Now, fischertechnik education products are designed to offer a progression. At the elementary level, specifically grades 2 through 5, there are curriculum-based options for introducing brief, achievable projects based around the areas of simple machines and introductory robotics and coding, and these are used for classroom activities, of course. At the middle and high school level, fischertechnik offers sets for performing different STEM-related activities around a progression of subject-specific models focused on areas such as, let's say, renewable energy, pneumatics, and physics, and of course, robotics. Fischertechnik also has more comprehensive standards-focused curriculum sets for offering a complete and fully integrated project-based STEM experience as a class unto itself. Now, for college classes focused on robotics and automation, or for vocational and technical schools, there are a series of pre-assembled industrial simulation and training models. Now, while the subject matter may become more advanced and sophisticated as you move through these different levels, the same building system and the same parts are used throughout all levels. Now here you will see a list of the various product lines that fall under the banner of Fischer Technic Education in order of how they appear in this progression I just discussed. Now again, for purposes in this presentation, we will focus on the two areas you now see highlighted in red, being the line of robotics-focused construction sets and also the line of pre-assembled simulation and training models. Now that said, let's begin our exploration of the Fischer Technic Education Robotics line. On your screen now, you see a list of the products in the line. Robotics Minibots, the BT Beginner, the Robotics Advanced TXT Controller, RoboPro software, Robotics and Electro-Pneumatics, the Robotics and Industry set, the Robotics Sensor Station IoT set, the starter set for Microbit, and of course the 3D printer set. Now this slide shows in boldface and red type the 7 construction sets found in the main robotics line. Each of these sets either focuses on a specific area of robotics, such as I mentioned, robotics and industry, or on a particular age range, such as the Minibot set, which is intended for younger students. And each includes instructions for building a specific progression of models related to that area. Now, please note that these sets, while all educational in nature, do not contain formatted curriculum, but instead each contains either printed teaching and activity materials, or else it'll provide you with access to downloadable versions of such materials. Now, the materials that I'm talking about are designed to provide teachers with suggestions for various experiments and tasks that students can perform with each finished model in class. The two items I didn't highlight before are the controller and the software, which are used with many of the Fischer Technic robotics sets. The Robotics TXT controller, shown in red here, is the interface or control unit for all of the upper-level Fischer Technic robotics sets, and the RoboPro software, also shown in red now, is the graphic programming software used for all Fischer Technic robotics. Now, these two items will be required for many of the sets that I'm going to discuss today, as well as either a Fischer Technic AccuSet or a Fischer Technic Power Set for powering the various models, all of which are available for individual purchase. Now, in a few cases, some of these models some or all of these items, I should say, are included in the kits themselves. But as we proceed through the presentation, I will let you know specifically when such items are required for use with the sets, or when they are already included in the sets themselves. So, going back to the robotics sets themselves, each of these sets are designed so that they can be used in a middle or high school setting, but there is no reason why they cannot also be used in a college class as well when exploring these topics. Each set comes packed in a sturdy plastic Gratno storage box, and each includes a printed full-color, step-by-step assembly manual for building each of the models, as well as additional teaching and activity materials, either in printed format, as I mentioned before, or available for download from the Fischer Technic e-learning portal. Also, as a rule of thumb, unless I otherwise note it, we would suggest that each set be used by no more than 2 students at a time, just to keep everyone engaged. Now, the first set in the Fischer Technic robotics line we'll look at is the Minibot set, and this set includes 145 parts for building 5 different mobile models. The set provides an engaging pathway for introducing students age 8 and above to the world of robotics. The models are all powered by an everyday 9-volt battery, and while the battery is not included in this set, everything else you need is, so no PC will be required here. The models in this set use a specialized pre-programmed robotics module. Students can select from different programs on the module by using a series of 5 sliding switches, also known as a DIP switch. Each switch is either placed in an up or a down position to select from the various programs. One of these options enables students to create a short motion program of their own by using 2 buttons and the Teach-In mobile robot. Students begin by learning about actuators, a component that performs some type of action such as the included XS motor. They will also learn about sensors, which do not perform an action, so to speak, but instead react to situations and events, such as a push-button switch or the infrared trail sensor. The first model students will build is a basic mobile robot. Students can control the speed and the direction of the robot by using a potentiometer located on the robotic control module. Next, students build a hindrance or an obstacle detector. The robot is constructed with 2 of the mini push-button switches acting as sensors. When this robot bumps into an obstacle it encounters in its path, it will back up and deviate from the path or the obstacle. Again, the direction of this deviation can be controlled through the use of the potentiometer. The third model is a trail searcher, which combines some of the attributes of the previous models with an infrared trail sensor. This enables the robot to follow a trail in the form of a black line. Students can use both the trail found on the pre-printed obstacle course that's included with each set, or they can use a magic marker to create their own black line path of at least 20 millimeters width for the robot to follow. The fourth model combines the hindrance detector with the trail sensor. And with this variation, the trail sensor reacts to a black line it encounters not as a pathway, but instead as an obstacle it must avoid. The fifth and final model allows students to build a teach-in robot. Now, teach-in is a concept from the world of robotics where a robot is moved to a series of desired positions which are each saved in a program, so that these same movements can be repeated easily in the future. Students learn how to run this teach-in created program either on a one-time basis or, if they prefer, in an endless loop. And that, again, is the Fischertechnik Robotics Minibot set, and you'll see the price right there on the screen. Now, the next set in the Fischertechnik Robotics line is the Robotics BT Beginner set. The BT in the name refers to the ability to build or to control the models via Bluetooth. This set includes 380 parts for building 12 real-world models, and it offers an ideal introduction to instrumentation and control for students age 8 and above. Students start off with an overview of the components that they will be working with. Now, as with the previous set we discussed, they will begin by learning about actuators, such as in this case the LED module and the access motor, before moving on to a brief overview of the sensors found in this set, specifically push-button switches and the phototransistor. Students will then learn about the types of circuits that can be made with the push-button switch. Next, students are provided with an overview of the BT Smart Controller. They learn about the 4 inputs for connecting the sensors, the 2 outputs for connecting actuators. They learn about the power connections, either a 9-volt power adapter or 9-volt battery, depending on what you use, and the ability to connect to the computer or tablet hosting the programming software, either using a USB connection or Bluetooth 4.0 connection. System requirements are either a computer using Windows 7, 8, or 10, or an Android tablet or smartphone equipped with Android 5.0 or higher. Now, do note that selected Bluetooth 4.0 sticks are also required for Windows 7. I should also mention the BT controller is also compatible with Scratch programming if you'd like to use that. Now, in any case, users are walked through the various methods of Bluetooth connection as well as the installation of either the RoboPro LT programming software for PC or the RoboPro Smart app for Android devices. Next, students are given an overview of the RoboPro LT software. They learn about the logic symbols or elements used to create their control programs, as well as the layout of the program's work environment. For example, the toolbar, the working screen, the test window, and so on. Students begin to explore the actual programming by working with the first model, that of a merry-go-round simulation. Using this model, students learn the basics of working with graphical programming software. They learn what a control program is. They learn how elements are added to a program and connected to one another. They learn about adding time delays and modifying actions, such as the direction of the rotation. They learn how a program is designed to start and stop, how it can be looped, and how a program can be expanded. Students explore further variables in programming with the building and control of a pedestrian light simulation. Now here students work with various settings such as the sequence of phases and the brightness of the traffic lights. The next model of a lighthouse with a blinking light allows students to explore the programming to address the 3 principles of lighthouse lighting. Students learn about the isophase principle, where the beacon is programmed so that the length of the light and dark phases are of an equal duration. The flash principle, where the light phase duration is programmed to be only a fraction of the duration of the dark phase. And the blink principle, where the 2 lights on the beacon are programmed to be illuminated for a different period of time, independent of each other. The refrigerator door simulation offers further programming challenges. Now here, students will be first asked to program the light to go on when the door is open, and then to modify this program to cause a red indicator light to start flashing when the door remains open for a specified period of time. The next simulation students build is a drum-style washing machine model. Now here, students will work with programming different cycles with variations in time, speed, and different direction of rotation, also with programming a safety switch for the door, and the programming of a text display to show the current cycle. The next model in the progression to be addressed is an automated hand dryer, which is programmed so that when a light barrier is broken, a fan switches on and remains on until the light barrier is no longer interrupted. The exploration of the use of light barriers continues with the construction and programming of a parking barrier that raises to allow vehicles to pass when the light beam is broken. Students will next build a trio of industrial simulation models. The first model, of a punching machine, requires students to program a safety switch, where the machine will only operate when two switches are held down simultaneously, along with the light barrier. The second of the industrial models to be addressed is a conveyor belt. Students program the belt to activate when the first of two light barriers is interrupted or broken, and to switch off when the second light barrier is breached. The final industrial simulation combines the functions of the previous two models. In this case, students will program the conveyor belt with punching machine to move a workpiece down the belt to be punched, and then reverse direction and move the workpiece back to the starting position. The final two models introduce students to mobile robotics. First, students will build a tracked vehicle. Here, they will be required to program the motors that move the tracks on each side of the robot to run at different speeds so that the vehicle will move in various directions. Students program various direction changes with different motion times. The final model adds a hindrance or obstacle detector to the tracked vehicle. Students are asked to build some simple obstacle courses out of materials that they have on hand, and then to program the robot to recognize and drive around these obstacles. The instructional material also includes a special section specifically on programming and controlling the various models using the downloadable RoboPro Smart app or for Android-based smartphones and tablets, and the Bluetooth feature. And that's an overview of the Robotics BT Beginner set. Once again, 380 pieces in all, including the BT Smart Controller and RoboPro Lite software for building 12 different models. We now step up to the main tier of the fischertechnik robotics line with our look at the Robotics TXT Advanced set. This set contains 310 parts in all, which includes the Robotics TXT controller and a license of the full RoboPro programming software. Once again, this all comes packed in a sturdy Gratnell storage box. Now, regarding the TXT controller, it is the most advanced controller yet created for fischertechnik robotic models. It boasts a full-color 2.4-inch touchscreen display, a combined wireless Bluetooth module, a micro SD card slot for additional memory space, an IR receiver diode, and an integrated loudspeaker. It also has 4 motor outputs, 8 digital analog inputs for sensors, and 4 high-speed numerical inputs. The TXT controller has 128 megabytes of RAM, 64 megabytes of flash memory, and a 600 megahertz processor. Now, as mentioned earlier in the presentation, the Robotics TXT controller can also be purchased separately, as it will be required for other sets as part number 522429. The RoboPro software is the full version of the programming software that is used for all the advanced fischertechnik robotic models, as well as for the 9-volt versions of the industrial simulation models that we're going to look at later in this webinar. Now, RoboPro is a graphic programming software which uses easily identifiable icons and a flowchart-style design to make programming easy to understand even for the novice. Now, it should also be mentioned that the software includes sample programs for all of the models that we're going to be building with this set. Now, with the aid of the RoboPro software, it is also possible to program your own apps for controlling the models with your Android smartphone, tablet, or PC. Students can visit the manufacturer's website for more information on this, as well as the fischertechnik e-learning portal using the access code included in the assembly instructions that you'll find in each booklet. The RoboPro software is also available for purchase separately in both single-user and unlimited school site licenses if you need either of those. Now, the contents of this set, with the addition of a fischertechnik AccuSet for powering the models, which is required and sold separately, will allow students to build 14 realistic models, including mobile robots and also robots incorporating vision systems. Now, the latter is made possible with the addition of the fischertechnik USB camera attachment, which is also included in this set. So just to be clear, the only thing you will need with this set to purchase separately will be the AccuSet for powering the models. Everything else is going to be included that you'll need. Now, once again, students start off by learning about the various different components that they're going to be using in constructing the robots. Again, they're going to first look at actuators, the components which perform some type of action, and examples of the actuators found in this particular set will include the encoder motors, the excess motor, LEDs, and the lens tip lamp. After this, students will examine the sensors that are going to be used, and the sensors, of course, act as the counterpart to the actuators. This is because, once again, they do not perform any actions, but instead react to certain situations and events. Now, examples found in this set will include the phototransistor or light sensor, will again include the push-button touch switches, will include an NTC resistor, also known as a heat sensor, and the previously mentioned camera module. Students will first progress through building and experimenting with a series of starter models, become familiar with the TXT controller and the software. And this will include things like a simple ventilating fan, a timed pedestrian light simulation, a hand dryer equipped with a light barrier, a temperature control where once the specified temperature value is exceeded, the fan is turned on, and an automated barrier, once again using a light beam that must be interrupted for the barrier arm to raise. After this, students will begin to explore the use of the camera and image processing with the robotics. The first model of the cameraman introduces students to how they can view what the robot camera sees on their own computers using the RoboPro software. They will also turn the cameraman into a motion detector. Now, in the process, they're going to learn how intense a motion must be to activate or actuate the sensor, and how extensive the motion must be in relation to the entire sensor field for the robot to react with a flashing alarm. Now, they're going to work further on this idea with the next model, and that's of a swiveling security camera, where a motion can be made to trigger an alarm which will sound through the loudspeaker of the TXT controller. Students begin to explore the area of mobile robotics by first building a basic mobile robot. They will learn about how turns and changes in direction can be programmed. They will also learn how the use of standard motors will only offer imprecise results and how greater precision and movement can be achieved with the use of the encoder motors. Now, with encoder motors, the rotation of the motor is measured with the use of a magnet and a sensor, much as a bike speedometer clocks the revolutions of the bike wheel. After this, students will create a mobile obstacle or hindrance detector. The robot will be programmed to back away from obstacles it may encounter, to move around them, and then resume its journey. Students will modify this model with the addition of the USB camera module to create a robot that can react to color and also share what it sees as it moves about in the world. Now, and with the use of a wireless connection between the TXT controller and the PC, students will also be able to control the robot remotely. The next model the students will build and experiment with is a trail searcher that uses the camera to detect and follow a path. This can allow for even greater precision in reacting to changes ahead, such as curves in the path. The detection robot combines several camera functions in one model. This robot is able to look forward to detect its surroundings. It's also able to look down to follow one of the various colored trails or an obstacle course, such as the printed one that is included. This robot also uses the NTC resistor to collect temperature data. Students can also download the TXT CamDroid application from the Google Play Store. This app allows them to connect the TXT controller to their Android smartphones via wireless, enabling them to remotely control the detection robot. For the final exercise, the students will build two variations of a soccer-playing robot. The first variation includes movement control, where the camera is mounted on a stand next to the robot, and the robot is taught various tricks, such as how to shoot a ball once it is detected by the light barrier, or how to react to movements made in front of the camera. For the second and final version, the camera module is installed directly on the soccer robot. And in this case, the robot uses a printed stadium simulation also included in the box. Students then go about various programming tasks to enable the robot to properly detect the ball and various markings of the stadium. By recognizing these markings, the robot is able to then properly position itself on the playing field with a higher degree of accuracy. So all 14 models that we just went over can be built with the Robotics Advanced set, which once again includes both the Robotics TXT controller and the RoboPro software. Now, as I mentioned previously, a fischertechnik AccuSet, which is sold separately, will also be required to provide power for all of these models. Now, the next two sets that we're going to review each contain parts for building specific types of robotic models and are essentially designed as add-ons to the Robotics Advanced set. Each of these add-on sets will require users to have a Robotics TXT controller, will require you to have the RoboPro software, and either the AccuSet or a fischertechnik power set for all models and activities. Now, the first of these two sets is the Robotics and Electro-Pneumatics set. This set contains 440 components, which, when combined with the items I just mentioned, will allow you to build 4 different electro-pneumatic machines and robots. The instructional material that accompanies this set begins with an overview of the principles behind pneumatics, which of course is known as the science of producing motion with air. Students learn how a pneumatic cylinder works, they learn how pressure is calculated, and they learn the process of generating and storing compressed air with the use of a compressor. Students then learn about using valves, such as solenoid valves, to control the flow of air to the pneumatic cylinders so that the cylinder either expands or retracts. They also learn about how electrical and pneumatic circuits, can interact. The first model addressed in the progression is a compressed air motor, which acts in a manner similar to a steam engine, except that in this case, instead of steam serving as the propellant, it's compressed air. Students then experiment with different methods of controlling the model. A manual control with the use of a push button and also incorporating a switching plate for continuous motion. After this, the model is wired to the Robotic TXT controller so that students can then explore how a program can be used to control this model. The second model is a simulation of a color sorting machine such as would commonly be found in an industrial setting. This model incorporates a vacuum suction device for stripping workpieces to move them about. It also incorporates an optical color sensor, which is used to sort the parts by measuring the reflected light from each piece, which is output as a specific voltage between 0 volts and 10 volts. Students learn that each color is assigned its own approximate voltage and how the sensor thus helps the machine to sort the parts by where each piece falls in this voltage range. Students learn how these color values are defined. Students also learn about the various sensors and actuators introduced in this model, including the use of a phototransistor and a lens tip lamp, which are used together to form a light barrier. They also learn about the electric motor and the vacuum pump, as well as how the control program and color recognition subprogram required for the model are created in RoboPro. The next model addressed, a ball obstacle course, utilizes a vacuum picker arm to automatically return balls to the starting position. The importance of accuracy of construction and attention to detail when wiring are stressed. Students perform further work with subprograms and learn about defining variables in a program. The final project created with this set is the building of a pinball machine simulation that pulls together all of the elements touched upon previously in one fun, and we should say highly sophisticated model. And that is the Robotics and Electro-Pneumatics set. The second of the two add-on sets is the Robotics and Industry set, which, like the previous set, allows you to build 4 different models, but this time, of course, focusing on simulations of the types of robots you might encounter in an industrial setting. This particular set contains 510 pieces, including aluminum struts for greater stability of construction. The teaching and activity PDF that accompanies this set begins with a brief overview of industrial robotics, their origin, and the many areas of production where such robots are used. For example, welding, cutting, measuring, grinding, stacking, assembling, and so on. Now, as in the previously discussed sets, an overview of the materials that will be used is provided, including the actuators, the sensors, the controller, and the RoboPro software. The first model to be built with and worked with is a gripper robot, which is designed to be able to raise and lower its arm and also to be able to turn. Robotic positioning is discussed, as well as specifying the position of the linear and rotary axis of the robot. Students are asked to create a reference run program and a flow chart. They will then revise positions or revise portions of this program. The second model built is a high bay storage rack, as is found in many modern warehouse systems. As the positioning needs with this robot become more sophisticated than the models we have discussed before, more subtasks are required, each of which requires a subroutine to be created in the robot's program. The third model addressed is a pivoting gripper, which allows you to create a robotic arm which can position work pieces at a different angle than they were originally picked up at. Now, once again, further positioning subroutines must be created by the students for this new pivoting action, building on the programming steps they have learned about in the previous models. The final model of a 3-axis industrial robot, or a pick-and-place robot as it's sometimes called, is used with a robotic gripper that can move in 3 different directions. Now, while the previous 3 models built were designed for very specific activities, the 3-axis robot is by contrast more of a multi-function robot, which can be used to perform various types of work. With the 3-axis robot, students work with the teach-in method used for programming industrial robots. Once again, this is where the robot is moved to specific positions using the controller, and the position is learned or saved and then moved to the next position, which is also saved, and so on. The sequence of saved positions together will comprise a program consisting of all of the various motions, which the robot can later perform by itself. Students will create their own teach-in program using this robot. Students will also learn about French mathematician Edouard Lucas and the puzzle he created in 1883 called the Towers of Hanoi. This puzzle involves the moving of plates, or work pieces in this case, in a specified arrangement. Students then use the 3-axis robot to solve this puzzle. And that's a look at the Robotics and Industry set. Again, like the Robotics and Electro-Pneumatics set, a TXT controller, RoboPro software, and a fischertechnik AccuSet or fischertechnik power set will be required for all operations. The next set in our progression is the Robotic Sensor Station IoT, which is available both as a complete set, which will include the controller, the software, the power supply, or there is also a version which, like the Robotics and Industry and Robotics and Electro-Pneumatics set, where each of these items must be purchased separately, or you're assumed to already own those. Now, the focus of this set, or sets I should say, is to provide students with an introduction to data logging, as well as cloud-based control, smart homes, and the Internet of Things. The downloadable teaching materials designed for this set begin with an explanation of some of the key terms. Digitization is discussed first, beginning with the roots of the term, which date back to the original computing machines created by Gottfried Leibniz in the 17th century. Essentially, the term originally referred primarily to the conversion of analog data into zeros and ones. The more modern use of this term refers to the storage and processing of data without using paper, such as, for example, the conversion of printed books into e-books, or of music saved as MP3 files. The term Internet of Things refers to the global networking of real and/or virtual objects using computers located around the world, which allows these real or virtual objects to exchange information with one another. The term smart home, also sometimes known as efficient living, refers to the networking of household appliances and such, things like heating systems, lamps, washing machines, and so on, so that they can be monitored and controlled from a central point. Finally, the term Industry 4.0 is discussed, which is somewhat similar to the idea of the smart home. Here, the process of producing specialized goods that meet a customer's particular criteria can be completely automated, even up to the point of preparing these goods for actual shipment. In cases such as this, the first actual human to physically interact with these goods might well be the person involved in delivering them to the end user. This is followed with a discussion of some of the components used and suggested work habits, similar to how these topics were addressed in the previous sets we reviewed here. The first activities will center around a simple model of a light with a brightness sensor. The idea here being that such a light can be used outdoors and the light itself controlled depending on the level of ambient light brightness. Now, this is a great activity for enabling students to become familiar with using the Robotics TXT controller, and is designed to take students step by step through the act of creating a program for the model using the RoboPro software. First, students will need to create a program for the robot where, as it becomes darker, the light turns on. Doing so will require students to experiment to determine a threshold value, which is a resistance value to be registered by the phototransistor, which will in turn cause the light to go on or instead turn off when a lower value is registered. Once students have created a successful version of the program utilizing these resistance values, they will then be asked to create a program where the three different lights on the model will switch on, one after another, as it becomes increasingly darker, until all three bulbs are illuminated when it is completely dark. The next model built will be a noise sensor. Here, students will utilize a sensor that is already built into the circuit board of the included USB camera attachment. With this model, students will be required to create a program that continuously measures the noise level, and as different decibel levels are reached, different indicator lights in either green, yellow, or red will need to be illuminated on the model. Designing the program will require students to utilize a subroutine. The next model will replace the USB attachment with an environmental sensor, an all-new fischertechnik component unique to this set, which will allow you to create a robotic wellness sensor. The new environmental sensor will enable the robot model to be able to measure such variables as gas, atmospheric pressure, humidity, and air temperature. Here, students will incorporate a special block in their programming containing both an init and a get block. Three different programming projects will be addressed with this model. The first involves the creation of a frost monitor. Here, the ambient temperature is to be continuously monitored. If the temperature falls below the value of 3 degrees Celsius, a red warning lamp is to come on, and an alarm for the TXT controller will need to sound once. In the second programming project, the model will be used as a mold monitor, where humidity is continuously measured. Here, the red warning light must be illuminated when the humidity is 80% or higher, indicating a danger of mold forming. In the third programming project, students will use the model as an air quality station. And in this variation, students will need to program the model so that the lights are illuminated differently to indicate different levels of air quality, from very good to bad. Next, students will work with a model of a stationary camera that includes an environmental sensor for data logging. The first project will involve programming the model to act as a motion sensor security camera, which causes an acoustic and visual alarm, in this case a sound from the TXT controller combined with the lighting of a lamp, to be triggered when motion is registered. The second exercise involves the introduction to simple data logging. And here, the values registered by the built-in brightness sensor are to be displayed graphically on an oscilloscope monitor, which can be viewed in RoboPro. The third exercise with this model will involve the logging of values collected as a spreadsheet program, where the data can then be displayed using, for example, a beam diagram. A fourth exercise will essentially combine the last two, where the data is displayed on the oscilloscope in RoboPro, and at the same time the values are saved in a CSV file for graphic display in a spreadsheet. The fifth and final experiment with this model involves a flower vase with soil and a seed being placed in front of the camera. Students must then create a program to measure the temperature, humidity, atmospheric pressure, air quality, and brightness. These values are to be measured every 12 hours and saved in a CSV file, and each day a photo must also be taken to provide further visual information on the growth. Next, students will construct a robotic barometer and program it so that the pointer on the model will point to a weather symbol, such as, for example, sun, clouds, or rain, corresponding to the current atmospheric pressure, depending upon the atmospheric pressure measured. The final model students will build with this set is a complete sensor station with a movable camera. This model will utilize various forms of data transmission: connection via USB cable, access point connection using wireless via Wi-Fi, computer to TXT controller, I should say, and the Wi-Fi client connection from the computer to a router to the TXT controller. The first programming project will involve using the model as a rotating surveillance camera, with the results viewable on a computer using the RoboPro software. Students will then learn how to connect the TXT controller to a PC using Wi-Fi. After this, they will learn how a Wi-Fi client connection can provide a greater range than a simple connection directly to the computer, depending, of course, upon the power of the particular internet router being used. The second project is an expansion of the first, where not only is the camera controlled, but the environmental data being collected is also displayed on the oscilloscope. As soon as the camera registers motion, an alarm is sounded. The next programming project involves learning how to connect the sensor station model to the cloud for the collected data to be displayed there. A special fischertechnik managed website is accessed where a dashboard monitor can display the various types of data collected from the environmental sensor, as well as the visuals from the camera. Students also learn how to control the camera itself from the dashboard monitor of this cloud-based site. Students see how they can control the model from anywhere around the globe with a smartphone, tablet, or any PC with access to the fischertechnik cloud via the internet. And that's the overview of the Robotic Sensor Station IoT set. Now, once again, this set is available in two versions. The first version, which has a part number of 544625, is once again, like the previous two sets we discussed, an accessory set that will require that you either have or purchase RoboPro software, a Robotics TXT controller, and either a fischertechnik AccuSet or power set. On the other hand, if you have none of those things and you want to be able to do everything we just discussed in this segment, the second version of this item, which has a different part number, 544937, includes everything that you're going to need to build all the models that we've just discussed. Everything being in the box, you'll be all set to go. The next set we're going to look at is a brand new release for 2019, and this is the starter set for Microbit, which is designed for teaching the basic principles of programming with Microbit single board computers for students in grades 3 and above. This set includes a selection of 90 parts for building 3 stationary automated models, along with the new fischertechnik Microbit I/O F5 adapter board with 8 outputs and 6 inputs. Please note that the Microbit controller itself, as well as the required control software and power supply, are not included here and will need to be obtained separately. The teaching activity materials for this set are downloadable from the fischertechnik e-learning portal. Start off with a brief overview of the Microbit itself, the I/O F5 adapter board, and the MakeCode software, which students will use to program and control the models. Students are told how to unpack the Microbit, how to access the MakeCode software using a web browser, and how to perform a functional test of the Microbit with the MakeCode software to ensure that everything is working properly. Students are also walked through a download of the program to the Microbit. They learn how a program is saved, and they learn how that file type must always be a hex file. Next, the materials discussed using the editor in the program. Students learn how the Make Code screen is divided into three sections: simulation, programming commands, and the programming screen. They also learn about the other important buttons found on the screen, such as the Start-Stop button for the simulator, the Download button, the Save Project button, and the Undo and Zoom In, Zoom Out features. Students also learn how to load partial or finished projects from storage media, how to import files, and how to browse for files. Blocks and commands are also discussed. Each single command, as with the individual blue lines you see on the screen now, are grouped into blocks based upon their function. In the example shown here, the 5 individual commands are grouped under the block called LED, shown in the column on the left. Next, the students learn about the first automated system they will build a simulation of, which is a traffic signal with a button that can be pushed by a pedestrian. The parameters of this system are discussed, such as what lamps are illuminated, the duration of the light, and so on. They then build their own version of this pedestrian signal with request button. Following the completion of this model, students are given a programming task where the system must be powered by a button on the microbit acting as a service switch. The light, which should normally be red, is only to switch to green when a requested button on the traffic light mast is pushed. The students are given a duration for the green phase of the lighting and other parameters, and they must begin to create their program using the commands in Make Code. Along the way, they are also taught about actuators, such as the push-button switch, and sensors, like the LED light. After the completion of the initial exercise, they will also modify the program to make the light flash. The next simulation model students are asked to build and program is a hand dryer with a light barrier. They will initially need to design a program where a user reaches through the light barrier to activate the motor with the propeller to start up, and when the same hand is removed, the motor stops. Here, students will incorporate the photo transistor and the motor light into the new model. Students also learn about digital and analog values and more about the different types of blocks used in the programming, such as basic blocks, pins, inputs, logic blocks, and so on. After this programming exercise, another program designed to make use of the LED display that is part of the microbit is also addressed. The final programming exercises are designed around the third model, a parking garage barrier with an arm that raises and lowers. The programming work in the initial variation of this model and a variation incorporating an optical display will be much more extensive than what students have encountered previously, now incorporating subprograms and loops. And that's our look at the starter set for microbit, and once again, the microbit, the software, and the power supply are not included. Now, the next item can also almost be considered a standalone item in the fischertechnik education family, and this is the fischertechnik 3D printer with an item number of 536624. Now, with this set, students can build an actual working 3D printer using the fischertechnik system. Now, please note that unlike many of the sets we have looked at so far, which can be used in a middle school setting or above, the 3D printer is specifically designed for use by students of age 14 years or older, essentially high school age and above. This set is designed to teach students the basic principles of 3D printing, which is also known as either additive fabrication or additive manufacturing. The activity materials created for this set, which are downloadable from the fischertechnik e-learning portal, begin with some basic information on the origins of this process. Students learn about the work of American inventor Charles Hall, who's credited as the originator of stereolithography back in 1980. This precursor to modern 3D printing was a process where light-sensitive plastic is cured by a UV laser. Further developments in the field were made by people such as Hideo Kodama, Carl Deckard, and others, whose work was vital in creating the industrial 3D printer which we know today. Scott Crump's experiments with glue guns during this period, which led to the birth of the FDM process, aka fused deposition modeling, is also touched upon. Next, we move on to an overview of the main components of a 3D printer and how they play a part in the process, starting with the extruder, the printing nozzle, the printing bed, the limit switch, the 3D controller, which it should be noted is an all-new controller designed especially for use with this set. It's not the TXT controller we've talked about before, and the material transport. Instructions on installing the print drivers and software on your window-based PC, which I should note is version 7, 8, or 10, are included as well as important tips on printer settings. The importance of calibrating and the printing head and printing bed is stressed. The adjusting of the Z-axis, which is a vital part of this calibration process, is spelled out. The steps involved with the loading and exchanging of the filament, which is of course the material from which the objects will be printed, is also clearly detailed. Now at this point, students will actually begin to get to print an object using the sample file provided. The file provided is in G-code format, one of the languages used for 3D printing and additive manufacturing. Now once the file is completed, students will also learn the process of safely removing items from the print bed. A sample from another file format, an STL file, which is a stereolithographic CAD file, native to the software created by the company 3D Systems, is worked with next. Students learn how such files must be prepared prior to the printing process with a slicer, which divides the object into thin slices and saves these slices as G-code. At this point, the tutorial material provides a little more background on the three primary 3D printing processes which currently exist: FDM, fused deposition modeling, or FFF, fused filament fabrication, which is the process used by the fischertechnik 3D printer, SLS, which is selective laser sintering, and SLA, stereolithography. The differences and advantages of each process are briefly discussed. The instructional material finishes up with an explanation of the differences in the G-code and STL file formats, a discussion of the PLA material or filament which is used for printing, sources on the internet for providing additional model templates to work with, and an overview of some of the types of design software for 3D printing, such as Tinkercad and SketchUp Make. This is followed by an overview of safety tips for working with the printer, as well as troubleshooting and maintenance information. Again, the fischertechnik 3D printer contains everything needed to get started, including the controller, the power supply, and the software, as well as a full color 44-page assembly manual and sample filament. Additional filament may be purchased separately as needed as well. And that completes the overview of the fischertechnik robotics line. And now we will move on to the line of fischertechnik industrial simulation and training models. Now, the line of industrial simulation and training models differ from the other fischertechnik products because they are not sets consisting of parts where the end user needs to build something, but are instead pre-assembled models mounted on a wooden base. Now, these are designed for use in colleges and universities, and also for training in companies and vocational schools. Now, besides this, they're also widely used by many companies for exploring and demonstrating IoT, for production and software development, for logistics and production planning, and for understanding automation systems. Each model in the current line of simulation and training models is available in two versions. There are 9-volt versions, which are most commonly used in an academic setting, and these models come pre-wired to fischertechnik Robotics TXT controllers. These controllers have also been pre-programmed using the fischertechnik RoboPro software, which we've discussed earlier. Now, with the addition of a basic 9-volt power adapter, such as the fischertechnik Power Set or another power adapter, the models are essentially going to be ready to use out of the box. So you unpack them, connect the TXT controller to a power source, which is, of course, not included. You turn it on and you hit the start button. Now, there is also downloadable activity material with more information on the components, which can also be accessed on the fischertechnik e-learning portal. Now, besides this, there are also 24-volt versions of the models, which will be most commonly used in industry or for higher level technical and vocational training. Now these contain 24-volt versions of components such as the encoder motors, the S motors, the compressors, the lamps, the solenoid valves, and such. Now these models will require a standard industrial PLC, i.e. a programmable logic controller, such as those that are manufactured by companies such as Allen Bradley, Siemens, Hitachi, Mitsubishi, and so on, for all the control of these models. Now as such, I have to note there is no programming supplied with the 24-volt versions, and the creation of all programming needed will be the responsibility of the end user. But as with the 9-volt versions, there is downloadable activity material which is available on the fischertechnik e-learning portal. We'll begin with a look at the 5 newest models in the simulation and training line. The first is the vacuum gripper robot. As you see, part number 536625 is the 9-volt version, which is wired to a pre-programmed fischertechnik's Robotics TXT controller, or part number 536630 is the 24-volt version for use with a PLC. This model is essentially a 3-axis robot with a vacuum gripper which can quickly and precisely position workpieces in 3-dimensional space. The next model is the automated high bay warehouse. Item number 536626 is the 9-volt version, once again wired to a pre-programmed Robotics TXT controller, and part number 536631 is the 24-volt version for use with industrial PLC. Now this model essentially acts as a simulation of a storage system similar to what can be found in many warehouses today. It has a transfer station with a conveyor belt and a shelf stacker for storing and retrieving special workpiece carriers from the 9 storage bins. After this, we have the multi-processing station with the oven. Part number 536627 is the 9-volt version, which in this case is wired to 2 Robotics TXT controllers, although only 1 power supply is required. Part number 536632 is the 24-volt version, once again for use with industrial PLCs. Now this model is designed to simulate a furnace with a pneumatic sliding door. The downstream processing station with a pneumatic transfer unit includes a vacuum gripper, a cutter simulation, a rotary table, and a conveyor belt. After this, we have the sorting line with color detection. Part number 536628 is the 9-volt version pre-wired to 1 Robotics TXT controller, and part number 536633 is the 24-volt version requiring an industrial PLC. The unit is designed to detect workpieces of different colors and sort them via conveyor belt into the designated storage slot. The final of the 5 newest models is the factory simulation, which essentially integrates the previous models, being the vacuum gripper, the high bay warehouse, the multi-processing station with the oven, and the sorting line with color detection into one self-contained material cycle. Part number 536629 is the 9-volt version, which is wired to 5 fischertechnik Robotics TXT controllers and will require 3 separate power supplies. Part number 536634 is the 24-volt version, again for use with industrial standard PLCs. I do want to note that this model is in very high demand and will sometimes have a lag time for fulfillment of 2 to 3 weeks. Also, due to the dimensions of this pre-assembled model, this must be pallet shipped as freight. Now, the other 4 models currently available are older classic models in the simulation line. The 3D robot, again available in both 9-volt and 24-volt versions, is a 3-axis robot with gripping forceps used to quickly and precisely position workpieces in 3-dimensional space. The conveyor belt is a simple transport belt, 275 millimeters in length, used for transporting workpieces with a diameter of up to 29 millimeters. These conveyor belts can easily be connected to one another if needed, and once again, this is available in both 9-volt and 24-volt versions. The punching machine with conveyor belt, like the name says, simulates the movement and punching of workpieces. The next of the models is the indexed line with 2 machining stations. This is a conveyor line with both a milling station and a drilling station simulation and 4 conveyor belts in a U-shaped arrangement. Once again, available in both the 9-volt version, pre-wired in this case to 2 Robotics TXT controllers, or a 24-volt version for use again with industry standard PLCs. Now, there is a final model, and it's brand new, and it was just released this summer, and this is the Training Factory Industry 4.0 model. Now, unlike the other models I've discussed, this is currently only available in the 9-volt version, with a 24-volt variation expected in late 2020. What the Training Factory Industry 4.0 is essentially a greatly enhanced version of the factory simulation model that we looked at previously, but this one has been modified specifically for IoT use with cloud control functionality built right in. Now, this model was designed with the focus for use on higher education, as well as an industry where solutions are needed for realistically demonstrating how automated processes can be monitored and controlled remotely. Among the features unique to this model are a Wi-Fi router, a calibration station, an environmental sensor for tracking environmental related data, a USB camera for remote visual monitoring, an NFC chip and NFC chip reader embedded in workpieces so that the exact location of the work cycle can be monitored, and the fischertechnik maintained cloud, complete with dashboard, where once again all the various processes can be monitored and controlled. The dashboard, which can be accessed and operated via mobile devices such as tablets and smartphones, as well as of course laptops and PCs, enables platforms to be viewed from 3 different perspectives: the perspective of a customer, a supplier, or the production view. Pages are sticking together here. And again, that's the Training Factory Industry 4.0, and I should say that that is now available. Now, I'd also like to mention that we have special customized storage and transport cases designed specifically for either of the 2 factory simulation models or the new Training Factory Industry 4.0 model. And those will be available, we hope, by the end of the year. And that essentially is the simulation and training line. Now, before we conclude today, I do want to touch very briefly on 2 more sets, each of which is covered in their own webinar. Now, the reason each has a webinar is that each of these sets comes with extensive, highly detailed standards-based curriculum for essentially offering a standalone robotics or STEM class or a long-term after-school activity. Now, that being said, while each is designed for conducting a curriculum-based program, they also serve as great all-in-one bundles of some of the most popular fischertechnik robotics sets, with everything you need to build a large group of models, from the parts to the controller, the software, and the power supply, all included in one box. The first of these 2 sets is the fischertechnik Robotics Competition set. Now, this curriculum-based set is designed to provide a pathway for exploring the subjects of robotics and coding through the focus of having students create mobile robotics of the type that would most commonly be found in a competition setting, whether at a local school level or even larger scale national and international competitions such as things like the RoboCup Junior. This set is designed around standards-based curriculum consisting of approximately 70+ academic hours of material. Each set contains 670 parts and components, which all packaged like the other sets we've discussed today in a sturdy plastic Ratnell storage box. When using the curriculum, this set is designed for use by small teams of 2 to up to even 4 students at a time. And again, if you would like to know more about the specifics of what this set addresses, I invite you to attend the webinar, which goes over all of that in detail. But for today, I just wanted you to consider the fact that this can be thought of as the ultimate fischertechnik mobile robotics set. Now, this one set will provide all the parts needed to build the models in both the Robotics Advanced set, which we discussed earlier, as well as a retail set called the Robo-TXT Explorer, which focuses only on mobile models, along with everything else needed. So this set will include the TXT controller. It will include the RoboPro software and the AccuSet for powering the models. Overall, you have 20 different models in all that can be built with this one set, and again, everything you need is right in the box. And the final set we're going to look at is the fischertechnik STEM engineering set, the contents of which you see here on the screen now. Now, the curriculum for this set is designed to provide a comprehensive overview of robotics, coding, and automation systems, in short, what we call mechatronics. Now, like the previous set, it is designed for use by groups of 2 to even up to 4 students in a classroom setting. It contains 890 parts in all, including, of course, the RoboPro software, the Robotics TXT controller, and an AccuSet, and once again, all of it comes packaged in a sturdy plastic Ratnell storage box. The standards-based curriculum targeted as a high school level class has a series of project theme units covering the areas of sketching and documentation, basic electricity, programming, sensing and vision systems, mobile robotics, actuators, and the fundamentals of automation and robotics. Now, the curriculum for this set is designed to provide enough academic material to cover over 150 academic hours. Essentially, this provides teachers with enough material to offer a standard 50-minute class period focused on STEM and robotics for 5 days a week, essentially a full academic year of material. Now, again, if you'd like to know more about this set or the standards that are addressed or the ways that the materials will be approached and so on, I, of course, invite you to attend our webinar focused on project-based learning. For today, what I'd like you to take away is that this one set, besides containing the curriculum that I just mentioned, also contains all of the parts and all the instructions needed to build all 22 models from 3 sets that we reviewed earlier, those being the Robotics Advanced set, the Robotics and Electro-Pneumatics set, and the Robotics and Industry set. Once again, this can be thought of as a great all-in-one option for obtaining everything you'll need in one box at a special price, even if you choose not to use the included curriculum. So once again, you have all the parts from all those sets, and you also have the controller, you have the software, you have the power source, so you have everything you need to build all the models from those sets by just buying this one set. So we've covered a ton of material here, and I'd really like to thank you for taking the time to attend today and the patience for me to go over all this and for sticking with us this far. Now, as I promised, I'm going to open up the floor for questions. If you do have any questions, please feel free to type in the chat window. I will go in and unmute if you would like to. And you are now unmuted. So feel free to type or talk or what have you. You can also email any questions you might have as you see up on the screen. You can email to me directly, lancez@studica.com. That's LANCEZ@studica.com. I will go once. I will go twice. And as I have no questions, I will thank you for attending today. So if you'd like to get more information